Hey guys, today we are going to talk about zeros and end behavior in polynomials, which should hopefully be some review from Math 3. So let's go ahead and get into this with our first example here. It asks you to find all real zeros. So today we are not going to be worrying about imaginary, just the real zeros. So, and I meant to be writing in that scenario. Another word for real zeros is going to be just the x-intercepts that you find in an equation. So we're looking just for x-intercepts with real zeros. So the way that you can do that in something like this example, the 2x cubed minus 5x squared minus x plus 6, is just to graph it and find the x-intercepts. So that's what we're going to do on Desmos. So I went ahead and came over here and graphed our equation, so 2x cubed minus 5x squared, etc. And I want to actually find those x-intercepts. So on Desmos, it's kind of cool. You can just come in and click on the points on the x-axis, and it'll give you all three of those x-intercepts for you. So you have -1, 0, 1.5, 0, and 2, 0. So I'm going to come back over here, and all of my real zeros in this were x equals -1, 1.5, and 2. And in a scenario like that, that is all you have to find. One thing I want to make a note of is remember that whatever the highest exponent is, whatever the degree of your polynomial is, that's going to be the number of zeros that you're looking for. Sometimes there's not going to be that many, and that can be due to either imaginary zeros or higher multiplicities. So that means that, like, say you have one of the zeros that's in your equation, that factor that created that zero was squared. So, like, for example, if you had like x minus 1, but then that was squared, then if you had a graph, then x minus 1 gives you the 0, x equals +1. So say that it's right there. Then on the graph in that scenario, then your graph would just come down and it would bounce on +1. That's what we called it in Math 3, was a bounce right there. So sometimes the multiplicities may be different and you won't find as many zeros because that would be considered like that 1 0 counted twice. So keep that in mind as you're looking through for all of the real zeros as well. Okay, so then working backwards from finding the zeros, you may be asked to write an equation from the zeros. So whenever you're writing the equation, you're going to have to come up with the factors. So the factors that are going to go into the equation, it's going to be x minus the 0 that you're given. And then if it has a multiplicity, then that's going to affect the exponent. So with that, we're going to start with number 1. So you would have y equals, and then we're just going to leave these in factored form for now. You may be asked to multiply them out and put them in standard form. But for the purposes of today, when we're just talking about zeros, we can leave them in factored form. So we're going to go through on each of these zeros. So x minus the 0 is 2. So I would do x minus 2. X minus -3 is going to give me x plus 3, and then just x minus +1. And then you can just leave the equation in that factored form, and that would be the answer to number 1. My next one, number 2, I would have y equals, and then I'm going to do x minus -1, which is going to be x plus 1. And it tells me that the multiplicity on that is 2. So all that I have to do with that multiplicity is put a squared on that factor. And then for 0, whenever 0 is one of your zeros, then that's going to give you just the factor x, because the factor would be x minus 0. That's just going to equal x. So then we have the factor x, and the multiplicity on that 0 is 3. So you would have to do x cubed. And Then the last scenario down here, we would have y equals, and the first one that you have is 1/2. So that would be like x minus 1/2. And then I'm going to come back to that. And then I would have x minus 4. And x minus -2 is going to be x plus 2. And there's a multiplicity of 2 on that one. But I need to come back to this first factor because you don't want to leave a fraction in your factors, because then whenever you multiply it out, your equation is going to have the same zeros, but it's not going to work out the way that you want it to. So whenever you have a fraction in one of your factors, so you have a fraction as one of your zeros, you're just going to take that denominator and kick it back up to the front. So that's how you're going to get the factor for that. So I'm going to take the 2 and kick that back out to the front, and I would have 2x minus the numerator, which is 1. And then I'm just going to drop my other 2 factors down as well. And you would have this as your final equation. So just be careful with that to make sure that you're not leaving fractions in there, and you'll just take whatever the denominator of the fraction is and kick that out to the front right there. Okay, so the next thing we need to talk about is end behavior. And end behavior is like if you have a graph, and I'm just going to sketch one over here, then it's talking about what is the graph doing at each of these ends. So like in the one that I just sketched over here, last year the way that we would have worded that is that the end behavior is down up, because on the left-hand side the graph is pointing down, and on the right-hand side the graph is pointing up. So then I just wanted to go over kind of like what is causing the end behavior in these situations. So it's going to be based on what the highest power of your equation is, or the highest exponent, and what the leading coefficient on that term with the highest exponent is. And so whenever we're going through this, if it's even and positive, the example I want you to think of is just like a positive x squared. And then that's just going to be a parabola, and so the end behavior is going to be up, up. So then if it's even and negative, then think of negative x squared. So that's going to be an upside down parabola where the end behavior is down, down. Then if your highest exponent is odd and it's positive, think of either just a line or think of x cubed. And if you have x cubed, the shape of that graph is the one that I actually drew down here. And so that end behavior is going to be down on the left-hand side and up on the right-hand side. And my last one is odd and negative. Think of like negative x cubed. And negative x cubed is going to be shaped kind of like that. And so on the left-hand side, it's pointing up, and on the right-hand side, it's pointing down. So that would be up, down. So if you didn't remember this from last year, take a minute to go ahead and jot this down in your notes. So then I just want to do a couple of examples of this. So on each one, you're looking for the highest exponent and the coefficient in front. So on the first one, my highest exponent is that 2. So the highest exponent is even, and my coefficient is positive. So that means that my end behavior is going to be up, up. On the second one, my highest exponent is this 4, which is even. And then on this one, my coefficient is negative. So the end behavior is going to be down, down. My next one, the highest exponent is 5, and the coefficient is negative. So if it's negative and odd, the end behavior is up, down. And my last one, my highest exponent is 3, and my coefficient is positive. So the end behavior is going to be down, up. So if you got confused on any of these, then look back at the chart from the table before. Make sure that you're just looking for positive or negative with the coefficients and even or odd with the exponents. So in Math 3, we were using those phrases up, down, up, down, down, and stuff like that to refer to end behavior. But now in pre-calc, we need to transition from using those phrases into describing end behavior in a different way or in a different notation. So what this is saying is, if you read this sentence right here, is as x approaches negative infinity, f of x approaches blank. And so what I want to talk about is, as x approaches negative infinity, that's just going to be whatever the left-hand side of your graph is doing. And then as x approaches positive infinity, that's whatever the right-hand side of your graph is doing. And just to get the notation down, I'm going to write x arrow, negative infinity. So that reads as x approaches. So that's the word that you're looking for, is approaches negative infinity. So this first part of this sentence, that as x approaches negative infinity, that's referring to whatever the left-hand side of your graph is doing. So whatever the first arrow you drew was. So we said that this was going to be up, up. This equation was the end behavior of it. So if it's up, up, then as x is approaching negative infinity, f of x, or y, is just getting bigger and bigger. So if it's getting bigger and bigger, then what it's going to be doing is approaching positive infinity. And so then for the second part, that's the right-hand side. That's going to be whatever your second arrow is. So as x approaches infinity, f of x, or y, is also getting bigger and bigger. So then that is also approaching positive infinity. So then on my next example, as x approaches negative infinity, f of x approaches what? So we said that this one was down, down. So down goes with my first sentence as it approaches negative infinity, and the other down goes with my second sentence. So then as x approaches negative infinity, y is getting smaller and smaller. So whenever it's getting smaller and smaller, it's going to be approaching negative infinity. And same thing on my right-hand side, as x gets bigger and bigger, y gets smaller and smaller. So it's approaching negative infinity. So then on my other two, quickly, we said that number 3 was up, down. So if it starts with up, then as x approaches negative infinity, f of x approaches positive infinity. And as x approaches infinity, f of x is approaching negative infinity, because that right-hand side of the graph is pointing down. And my last one here was, as x approaches negative infinity, the end behavior was down, up. So as it's approaching negative infinity, f of x is also approaching negative infinity. And as x approaches infinity, f of x is also approaching infinity. So that just says on the left-hand side of the graph, we're pointing down, it's getting smaller and smaller, y is getting smaller and smaller, so it's approaching negative infinity. And on the right-hand side of the graph, y is getting bigger and bigger, so it's approaching positive infinity. So just make a note of this type of notation for end behavior. All right, so then there's one more thing I want to go over, and it's similar to what we were doing in the beginning. We're still writing equations from the zeros, but this time it's going to give us a specific end behavior. So we have to make sure that the equation that we write has that end behavior. So starting with number 1, we have zeros at 1, negative 1/2, and 3. So I'm going to start by just writing my equation. So y equals, the first factor would be x minus 1. For the negative 1/2, it would be x plus 1/2, and then you would have to kick that 2 to the front, so it would be 2x plus 1, and x minus 3. But then it tells us the end behavior is, as x approaches negative infinity, f of x approaches negative infinity. So the left-hand side is going down. And as x approaches positive infinity, f of x approaches positive infinity. So the right-hand side would be going up. So if you're looking for an equation that has end behavior down, up, that's going to have a positive coefficient and an odd degree. So that means that if you multiplied all of these factors out, then the leading term would have to be odd and positive. And if you were to do that, then the leading term, since there are 3 x's, would be x cubed, and it would be positive. So you don't have to change anything on this one based on the end behavior. You can leave it as x minus 1 times 2x plus 1 times x minus 3. And then we're going to move on to number 2. So we have a 0 at x equals 0. So like we said before, that's just going to be an x. And then times negative 4, so that's going to be x minus negative 4, which is x plus 4, and x minus 2. And then it tells us the end behavior is as x approaches negative infinity, f of x approaches negative infinity, and as x approaches positive infinity, f of x approaches negative infinity again. So this one is down, down. So we know that the highest exponent needs to be even, and the coefficient on that term needs to be negative. So if we multiplied out the x plus or times x plus 4 times x minus 2, then x times x times x is going to give us x cubed, and it's going to be positive. So one thing that we need to change is that we need to make this negative. And let me do this in a different color to indicate that we are changing things about it. So we need it to be negative. So now we have a negative x cubed. But then we also need both ends to be pointing down, so we need the highest power to be even. So that means we need to change the multiplicity on one of these zeros to make that highest power even. So I'm just going to change it on the x that's in the front, and I'm going to make it squared. So then if we multiplied negative x squared times x, then we would have a negative x to the 4th, which would have the end behavior down, down, which is what we're looking for. So that's what it means whenever it says to assign multiplicities as needed, is you just need to throw an extra exponent in there somewhere, essentially. And if you are able to do that, it doesn't matter which of the factors you put it on, but just make sure that if you were to multiply it all back out, that you get a leading term that would have the correct end behavior. So then on my last one, we would have y equals, and we have our first 0 at 5 over 2, so that would be like x minus 5 over 2, but then you need to kick that denominator of the 2 back to the front, so it would be 2x minus 5, and then times x minus negative 3, which is x plus 3. So then if you were to multiply that out at this point, then your leading term would be 2x times x, which would be 2x squared. And then the end behavior that it's asking for is for as x approaches negative infinity, f of x approaches positive infinity, so that's up. And then as x approaches positive infinity, f of x approaches negative infinity, so that's down. So we need the leading coefficient to be negative for 1 because it's up, down, and we also need the highest exponent to be odd. So to get that leading coefficient to be negative, you can just throw a negative out in the very front. You don't have to put it with one of the factors if you don't want to. You can literally just put it in the very beginning. And so then now your leading coefficient will be negative. But we also need it to be odd. So you're just going to want to assign a multiplicity on one of these zeros. It doesn't matter which one. So I'm just going to put an exponent of 2 on my x plus 3 term. So now I would have a negative out front, and then you would have 2x times x again, which is going to change that degree to 3. So that's how you would go about working on these types of problems, is you may just need to throw in an exponent or throw in a negative in comparison to how we were doing it at the beginning. So let me know if you have any questions on zeros or end behavior, and we will try to work on those as we need to. But hopefully the majority of this, other than just the notation, was a good review from Math 3. In behavior and zeros.